Welcome to ArgMin, the minimal value YouTube channel with minimal value mathematical videos for frustrated mathematicians and mathematics students. This is the real analysis course. We're on lecture 9, covering series convergence and rearrangement. So let's define what a series is. So we know it's a definition. Let's write down definition. Let an be a sequence in R we define the series to be summing from n equals 1 to infinity all the elements in the sequence, or sometimes you write as shorthand just that without the upper and lower indices or the limits of the sum, I guess. And that will look like a1 plus a2 plus a3 and so on, provided the sum exists. Yeah, that's hard to say. Definition, another one. Given an, let sk equal a1 plus a2 all the way up to ak. We call sk the sequence of partial sums of this series. Let me just write that K so you can actually read it. We call SK the kth partial sum. Just highlighting, we're not defining sequence, we're defining sequence of partial sums, and kth partial sum. That looks like that, and the kth partial sum looks like that without the parentheses around it. And I'm gonna hit you with another definition. We say an, the series converges if sk, the sequence of partial sums, goes to L. We write sigma an is equal to L if sk diverges. We say the sums diverge as well. So now we define convergence and divergence for a series. Let's look at an example. Something you might have seen before. 1 over np is called a p series, sometimes a geometric series. Converges if and only if p is greater than 1. So proposition, if an converges, then the sequence must have a limit of 0. Proof. Suppose the series converges. Let Sk be the kth partial sum of the series. So Sk has limit L for some real L, because we're saying the series converges, so the sequence of partial sums must converge to some L. This implies that an is equal to the nth partial sum minus the n minus 1th partial sum, just from how partial sums work. This sums from 1 to n, this sums from 1 to n minus 1. So if you subtract that off, then you only have the nth term, an here. So as the limit increases, or as these go to the limit, they're going to be like that. That's an equality, which is equal to 0. And that proof is done. Now we're going to go theorems on the series called the Cauchy criterion of series. If sum of an, the series, is a series, then the following are equivalent. I'm just going to write it that way from now on, because we might see a lot of these coming up. An converges. 2, for all epsilon greater than 0, there exists n natural number such that the absolute value of everything from k equals n plus 1 up to infinity. Let me just extend that so it's more clear as an absolute value. Let's clean the line up. Is less than epsilon. And 3, I forgot to say what that was valid for all n larger than that constant n. So also for epsilon greater than 0, there is a natural number big N such that the sum from k equals n plus 1, it's really ugly, k equals n plus 1 to m of ak, absolute value of that is less than epsilon for all m greater than or equal to n. And what this term is, it's just the limit minus the nth partial sum. And what this term is the nth partial sum minus the nth partial sum. And let's look at reasons why this is true. And before we go into that, let's go into what this means. So saying the following are equivalent means that one implies two and 3. 2 implies 1 and 3, and 3 implies 2 and 1. So if you know one of these is true, they're all true. We won't go into detailed proofs, but here's a rough idea of why it's true. So 1, AN convergence means SN goes to L. 2, that's just the same as saying L minus SN goes to 0. It has a limit 0 because that inside is L minus SN. So if you subtract 0 and take the absolute value, that's less than epsilon. That means that the 0 is the limit of this sequence. And 3, SM minus SN is less than epsilon. So we're saying here that SN is Cauchy. Similar to the previous one, that's true because this is SM minus SN. So yeah, it converges. So it's Cauchy. Yeah. Now let's talk about absolute convergence. It's related to convergence, but it has a little twist to it. As you can maybe tell, there's going to be absolute value signs. We say a series converges absolutely if, AN converges, so if you take the absolute value of everything in there, and if AN as a property, that's the end of the definition there. If AN converges but not absolutely, we say AN is conditionally convergent. This is a separate definition. Oh, highlight, don't erase. So let's propose the following statement. If a series converges absolutely, then it also converges. It's a bit of a long proof, so I'll have to move down, but let's keep those definitions in mind as you go through the proof. So suppose AN converges absolutely. So this series converges. Let Tn, I forgot to say this was part of the proof. equal the partial sum of the absolute values up to n. We know Tn, the sequence of Tn's goes to L in R. So now need to just close that. Let epsilon greater than 0 be given, since Tn converges, it's Cauchy. So there exists an natural number such that Tm minus Tn less than epsilon for m greater than or equal to n greater than or equal to n. That's just the same thing as saying for m greater than or equal to n greater than or equal to big N, am plus am minus 1 all the way to an plus 1 is less than it's an epsilon. Let Sn be the partial sum for all n in n. If m is greater than or equal to n is greater than or equal to big N, we have Sm minus Sn is equal to am plus am minus 1 plus all the way to an plus 1, and that is less than or equal to the absolute value of each term by the triangle inequality, going down to an plus 1. And we have that from here that is less than epsilon. Right, so to walk through that proof, we're saying if this series converges absolutely, we want to show that it converges. And we had a powerful technique from the previous lectures that to show convergence, we don't need to know the limit anymore. We just can show, use some Cauchy properties. So let's suppose it's absolutely convergent, as in the hypothesis of the proposition. So this series of absolute values converges. We define these partial sums. And since it converges, we know there's some L in R that it converges to. And now we show that it's converging, that the series converges. So let that be given, since that is Cauchy. This series is, since the series is converges, it's Cauchy. So this holds for the series, and thus if we expand out the definition for Tm minus Tn, we get that Tm is a1 absolute value all the way to am, and you subtract off Tn, which goes from an down to a1, so that gives us the absolute values of m down to n plus 1. Now we look at the partial sums and then compare them, and then we look at that by just expanding this sum out, and that's less than or equal to the sum of the absolute values by the triangle inequality, which is less than epsilon. So then I guess we should write, just for completeness sake, therefore the series AN converges. Okay, now let's talk about rearrangements. Rearrangement of the series is a series A pi of n, where pi is a permutation of n. So it's just a natural numbers but rearranged. Thus the name rearrangement. So for example, an, this series, that's defined as 1 over 1, 2 squared plus 1 over 3 squared plus 1 over 4 squared, and some whatever terms. Rearrangement of that would be if you just swapped the spots for these terms and all other terms being equal. So Bn, the series of Bn's, is a rearrangement of the series of An's. I'm kind of sick. My voice is very bad right now. So S, that's another example. Let S be the sum -1 to the k plus 1 over k. This is conditionally convergent because it stops oscillating, and then so it just goes, so you have a sum of 1 over n plus just a standard sum going to 2. We know that S is greater than 0, and let's keep that definition up there. Assume every rearrangement of -1 k plus 1 over k converges. So 2s where'd the 2 come from? It's equal to 2 minus 1 plus 2/3 minus half plus 2/5 minus 1/3 plus 2/7 minus 1/4, and so on. So these are grouped together, and these are grouped together, and so on. Before we get lost, let me just see what is happening in here. I'm not quite sure about the last step. Series. And I'll take a sip of water while I'm scrolling through my notes. Okay. Still a bit lost. AN. But let's just keep going. I'm not sure where this 2 came from, but this is a rearrangement of this series. So if you take those sums, that's 1 minus a half plus a third minus a fourth, which does go down to 0. So it converges. But that is a contradiction. I guess we just wanted a contradiction. Assume, let me just write that down. Assume for eventual contradiction. So then that means 2s equals s, means 2 equals 1, a contradiction. So there must be some rearrangement that doesn't converge. Oh, I think I misspoke. I think I forgot this was conditionally convergent. So conditionally convergent means that this converges, but not if you take the absolute values, because it will diverge to a larger number. But if it's not absolute valued, then things are alright and it converges. We're not going to be worrying about convergence tests in this class, but you should just know how to tell if a series converges. So for next class, we're going to be proving this proposition, the following proposition. I'm just going to introduce it now. Every rearrangement of an absolutely convergent series converges to the same limit. Excuse me. All right, that's it.